application to do blockchain. And actually not really, because the main difference which will become important in this talk is that in SMR we have a single trusted application. Like if we replicate the crash tolerant, then replicas are trusted. If you replicate Byzantine tolerant, replicas are not trusted, but the application itself is trusted. Unlike in blockchain where we have multiple applications living on the same blockchain, which are deployed by the third-party application developers, so they are not necessarily trusted. So this slide gives you a bit of history and also sets where Hyperledger Fabric stands. So it all started with Bitcoin with this hard-coded cryptocurrency application with very limited ability to extend this application. And Bitcoin came with a native cryptocurrency and expensive proof-of-work consensus protocol. Then it was extended by Ethereum to support these arbitrary applications, so-called smart contracts, right? But it also retained native cryptocurrency and proof-of-work consensus, right? So where Hyperledger Fabric comes in the game is that it takes the idea of Ethereum, but in Ethereum you need to code applications in a domain-specific language called Solidity, and we'll see why later on. So what we do in Fabric is we give the ability to blockchain programmers to code in general-purpose languages. We currently have support for Go, Java, and OJS. We don't have a native cryptocurrency because in many use cases you actually don't want one. You don't want to rely on volatility of a cryptocurrency. And we have a modular and pluggable consensus instead of the hard-coded proof-of-work consensus. So what is the main novelty in Hyperledger Fabric? So to understand this, I'm talking a bit about how blockchain state-of-the-art works. And basically all blockchains work following the order execute architecture. So order execute means you order these input transactions using total order consensus, right? And then you execute them in each node at the end of ordering, right? So this is known in this community as active state machine replication, and many protocols that we have follow this pattern. So including Paxos, including many BFT protocols. So for permissionless blockchains where you don't have, essentially you don't have node identities, this order execute architecture looks as following. So you have proof of work block mining, where miner tries to solve a cryptographic puzzle which is fairly complex and consumes a lot of energy, right? In order to find a valid block. So this typically consists of finding a nonce such that the hash of the block is smaller than some difficulty, which is a very small number. Then this block, when it's found by the miner, is disseminated via gossip along the network. And what all the miners do in the end is they need to validate the block, which consists of executing all the transactions in the block and just doing a simple hash to validate the block. So essentially this is one example of order execute, because we order first using this consensus called proof of work, and then we execute transactions in order at every node. In permission blockchains where you actually have node identities, it looks a bit differently. So you have a more greener protocol that is also more chatty. So one example is to use something like PBFT from Castro Lisco or any other BFT protocol, right? Where you essentially don't have intensive computation, but you replace it with a lot of network computation, right? But it's the same protocol because you run the ordering consensus protocol, and then once you reach the order on the messages, then you execute, right? And this happens also for all the nodes. So again, this is an example of order execute architecture. So to repeat the key requirements for Hyperledger Fabric, this is no native cryptocurrency, ability to code applications in general purpose languages, and to have modular consensus. So it might not seem intuitive, but what we have to do is essentially to satisfy all these things is to re-architect blockchains completely. So our blockchain doesn't look like order execute that I showed here. And the end result is Hyperledger Fabric, which is an open source blockchain. It's available on GitHub under permissive Apache 2 license. So what are the issues with order execute with Hyperledger Fabric goals in mind, right? So one of the issues is this sequential execution of transactions on smart contracts on each and every node, right? So now you don't have a trusted application. Anybody can come with a like very slowly executing application or even a denial of service application. I can code an infinite loop application. It needs to execute on all nodes, right? So what blockchains do is they will make you pay you, for example, Ethereum, they will make you pay you for each step of computation. But this is tied to a cryptocurrency that we don't have now anymore because we want a blockchain without cryptocurrency. So we cannot use this trick. The other issue is non-determinism. So every basically blockchain or state machine replication paper will start with assumption that the application is deterministic. Now you give somebody ability to code a program in an arbitrary, in general purpose language, and suddenly this is not the case. You iterate a map in Go, it's non-deterministic. You look at the system time, it's non-deterministic, right? So how normally what you would do in blockchains, for example, again, Ethereum, this is just an example, you have a domain-specific language which compiles to a deterministic Ethereum virtual machine, and you execute EVM bytecode on Ethereum. And of course, if we want to support general purpose languages, this won't fly. There are other issues, like consensus protocols are hard-coded. I already mentioned this. Confidentiality is an issue. In order to execute, you somehow execute on all the nodes. And sometimes you want actually to restrict this execution to a subset of nodes. And you have inflexible trust models. For example, in permission blockchains, such as those based on PBFT, the assumptions of the underlying consensus, such as 3F+1 assumption that PBFT comes with, extends to applications. So we also wanted to be more flexible with this. So in one slide, what we did, we replaced this order execute architecture with a different architecture. So we're not ordering input transactions and they're executing transactions against smart contracts sequentially. So what we are doing is this. So we execute, order, and validate. So we first execute. This is the point where we execute untrusted code from application developer, mostly to remove non-determinism. So we execute first, we remove non-determinism, we transform the execution to updates that the application makes to the state. The state is modeled as a key value store. So we generate the read sets and write sets, and then we agree on the updates that are generated by the execution of potentially non-deterministic code. Then we order, but we ordered updates, we don't order inputs, right? We order these read-write sets statelessly, so the ordering service, as we'll see, doesn't really look at transactions, but really acts as a distributed sequencer, and then we validate. We'll see this in more details in the next slide. So essentially, an application in Hyperledger Fabric consists of two components. One is the execution code, which we call code that we call chain code, and the other is validation code that we call endorsement policy, and we'll see a bit of both towards in the rest of the talk. Okay, so how does this execute, order, validate architecture looks like? So it starts with a client that sends to a subset of peers a transaction for execution, right? These peers are called endorsing peers. Their number is really dependent on the distributed application, as we will see. So these nodes then execute the code. They actually execute without persisting any result of the computation. They really simulate the code. The chain code lives in a Docker container and is executed against the local state in a key value store which sits at the peer. Once the peer simulates the execution, it sends the signed response, which contains this read set and write set, right? The effects of the execution back to the client. This is ordered, so client waits for a sufficient number of messages. This sufficient number really depends on your application. And this is where the flexibility of the trust model for application is actually completely decoupled from the trust model from the ordering service. We'll have some examples later on. So the client then submits the read and write sets to the ordering service, which acts as a black box. In a sense, it doesn't look at the contents of a transaction, but really acts as a serializes all the transactions and makes this blockchain data structure. Then, basically, the results, the ordered transactions in a block come to the peers, and peers do the validation of a transaction. So there might be peers that actually don't execute the transaction in the first place, but all peers validate the transaction. So what they validate? They essentially validate whether whether the endorsement policy, which dictates how many responses client waits, is satisfied. So this is the piece of code that can be basically changed. You have an application, it can select one endorsement policy. You had another application, it can select another endorsement policy. It also imposes serializability on the read-write sets and finally commits the transaction. And this is actually the point where the effects of the transaction are persisted to the local state at the peers. Okay. So this is, well, the first phase is execution phase. The ordering service, what it does is the ordering phase, and this is the validation phase. So, back to distributed applications in Fabric. They consist of these two pieces. One is execution code. So this is the code, again, developed by third-party application developers. It's executed pre-consensus, and it can be non-deterministic. This is not to say that you should code non-deterministic applications. But if you do, actually what may happen in our architecture is that non-deterministic transactions are not live. For example, you may require that two executing peers, co-endorsers, execute the transaction in the same way because you want some Byzantine fault tolerance there, right? But your transaction rolls the dice, and you cannot get ever two nodes to execute the transaction in the same way. So this means that this transaction, because it executes against non-deterministic code, is not live. Unlike in the previous architecture where you're not guaranteed to be safe. And if you execute post-consensus, the fact that you did consensus is thrown to the water. The second part is the deterministic validation code. It cannot be deployed on the fly during the runtime of the system by an untrusted application developer, but it can be modified by a set of administrators. And here, administrator is really loosely defined. It can be defined as a majority of nodes in the network or whatever is the endorsement policy deployment, basically, however we govern the deployment of this code. So it's a more protected code, if you will. It can be only instantiated via chain code. And some examples include, for example, we have K out of N. Application specifies is an endorser, and we require that K out of N actually execute the transaction in the same way. We can have more elaborate endorsement policies, or we can have something, for example, that even takes a certain signatures if you modify a certain key in the key value store. And this is how we implement Fabcoin, and details are in the paper. So Fabcoin is a Bitcoin-inspired cryptocurrency that kind of mimics Bitcoin in certain ways, except that it emulates central bank emitting money, so like fiat emulating money. It doesn't give reward to the miners. And we have the details in the paper. Or you can have any customized validation code, right? It's just how you deploy this is more protected. And in the terms of replication, passive and active, we essentially have hybrid replication. It's a mixture of passive, like execute and then agree on the updates, and execute after consensus. So this is where basically we mix passive and active to hybrid replication. So for consensus, it's modular and it has total order semantics. So currently we have two implementations. One is centralized. If you want to deploy and develop around Hyperledger Fabric, you would do that. We have a production-ready crash fault tolerance and a proof of concept BFT developed together with University of Lisbon. This appears in DSN. So many more to come. Production-ready BFT ordering service is coming this year. And then we have some efforts to transfer some recent OSDI and Eurosys paper into Hyperledger Fabric ordering services. And if you're working on this, please try to plug in here your new bestest consensus protocol, right? So a bit about performance. It's really not. It really depends on the network. It really depends on the workload. But at least for Fabcoin, to give you some hint, for example, to compare to Bitcoin 7 transactions per second or Ethereum tens of transactions per second, we deployed this and reached, depending on the CPUs that are available to the peers, up to 3,500 transactions per second. And we also scaled the system up to 100 peers, which is for many applications sufficient, but we plan to go further in future work, right? Yeah, so with this last slide, that shows just a few of basically companies and consortiums that are using Fabric. It's used in over 100 deployments now. Many of them are proof of concept, but there are actually few production systems as well. I will take your question. Thank you very much.
Time for questions. All right.
So this is Gustavo Alonso from ETH. So on the performance results that you had, you said if there are 32 CPUs, right, on every node, right? What happens if you have different number of CPUs on different nodes, right? I mean, will you have a straggler effect that all of a sudden, because somebody is slow, everybody is slow? Because 32 are a lot, right? I mean, unless you have in mind only industrial applications with large servers.
So now I can spend more time on this slide. So basically, the dashed line is latency. So you see that with 4 CPUs, actually the latency is high, which transforms to the low throughput, which is at the order of 1,500 transactions per second. Then you would have our current bottleneck, at least with Kafka ordering service, and it would be with existing BFT ordering services, would be validation. So this is where we actually verify a lot of signatures. So in this case, you would have on this peer that has less CPU. If you have really a lot of load, you would actually have some queuing, and this peer would actually have lower throughput. But those that have more CPU will actually be able to reach higher numbers.
Thanks.
More questions? All right, so I have a question. So is the execute order model is like prone to live lock in your case? Is it because it may happen that a client may fail to get sufficient number of endorsements? So what happens in those cases?
Then, I mean, so if this happens for whatever reason, it can happen because of non-determinism, it can happen because of just some partitions. The client cannot reach the endorsers. It's up to the client to retry the transaction.
And can client can do some tricks like, for instance, Eve had some sort of a mixer kind of an optimization strategy to actually make it go through common cases.
Yeah, so this is so a lot of our architecture is actually based on Eve. We don't have a mixer in a sense that we try to, so there is a partitioning that normally you will have different endorsement nodes for different chain codes. So already you have some partitioning, so you should have across chain codes not a lot of collision, and the namespace is actually partitioned per chain code. You can have a lot of collisions depending on your programming model on a single chain code if you, for example, have concurrent transactions updating the same key. You can code around it using the UTXO programming model, or wait that we actually do something to actually improve concurrency, in this case for chain codes. We need to, so it's a complex system, and it's also open source, so we are trying to actually gradually improve the system, but this is what we have for the moment.
So we have time for one more question. If not, then, we have one here.
Hi, Jaime Dias from Inestec. I didn't understood quite well what is the incentive for the nodes to participate in Bitcoin or cryptocurrencies, blockchains based. I understand it quite well, but in this case, I'm not sure, for instance, if some nodes may just try to drop some contracts depending on the origin and benefit other ones, because it's not about money directly.
Yeah. It's a great question. So there is no, by the way, so there is no one single deployment of Hyperledger Fabric. It's meant for multiple deployments and instances. And your answer to your question will really depend on the use case and where is this deployed and how it's used. Many times, for example, in the first use cases that we have, nodes are altruistic because there is a company that actually runs the nodes and subsumes some cost without actually worrying about the cryptocurrency. If you want a public deployment of Hyperledger Fabric, for example, public ordering service or something like that, one needs to answer your question. How it will work, let's see. We decouple system design from incentives, but of course, in some deployments you want to put incentives back, and Fabcoin is the first way to go in that direction, right? Because it gives you the coin back that we just removed, right? From the system design, it gives you back, and then you think about incentives. But it's a great question, and my answer is it depends.
Okay, thank you.
All right, so let's thank Marco one more time. So before the next speaker setting up, I'm still missing the third speaker actually. So speaker for the third paper here, if he's around, he or she. So our next talk is from a joint collaboration between NYU and Tsinghua University in China, and the work is about making the inference engines in neural network improve the latency in the inference engines in neural networks. And this will be presented by Ling Fa. who is a PhD student at NYU. So,
Thank you for the introduction. Hi everyone, I'm Lin Fanyu from New York University. This is a joint work with Ping Gao, Yongwei Wu, and Jianyang Li. So in the past few years, deep neural network has rapidly matured from research prototype into real-life products. For example, Google Translate service uses neural network to improve translation. Reportedly, Google Translate service translates 100 billion words each day, which is more than 1 million words per second. The typical life cycle of a deep learning application is composed of two phases, model training and serving. Take translation as an example. In training phase, some corpus is collected and the many batches of samples are fed to the network to optimize model parameters iteratively. In serving phase, the learned model is deployed with weights fixed to predict the output of given input. Model serving has different performance requirements compared to training. Training is offline, and a huge amount of data are collected beforehand. The ability to process massive amount of training data is the key to finding the optimal weight. Therefore, training only requires high throughput. But when serving a model, the weight parameters are fixed, and the requests arrive from time to time. So in addition to good throughput, low latency is of great importance. In our work, our main target is improve latency of model serving. Also, our work only targets one type of neural network, which is a recurrent neural network. Recurrent neural network is one of the most important categories in deep neural network, which models the mapping between variable length sequences. Recurrent neural network is widely used in areas like translation, speech recognition, and question answering, and so on. Recurrent neural network takes in an input sequence and a function f, and recursively applies that function to the input sentence to compute the output h. When recurrent neural network is used, the computation graph will be unfolded. Each step takes in one element from the input sentence. The function f is called an RN cell and is parameterized by weight parameter theta. In our later experiments, we will always use the most famous LSTM cell as function f. What is important here and what we will leverage later is that the computation for each RN cell are identical and they all use the same weight. Translation model is based on recurrent neural network, but it's quite sophisticated. To simplify explanation, we consider a simpler model used for sentiment analysis. Here, the RN model takes in a sentence and tries to predict whether the sentiment of the sentence is positive, neutral, or negative. Now the input sentence is I love Porto. The computation graph is unfolded in 3 steps because the input sentence has length 3. Initially, the model starts with neutral. The model loops over the input sentence and applies function f to compute sentiment based on the previous output and the current word. In this model, only the output of the last step is of interest. Then how should we serve this type of model and guarantee low latency? Since the main target is latency, people may ask, why don't we just serve one request at a time, which seems to produce the lowest possible latency? This is true when the workload is low, but the naive solution produces terrible throughput because it cannot fully utilize GPU. So it cannot handle heavy workload. To give you a better understanding of the importance of batching for serving RNN, this figure shows a benchmark of LSTM computation. As you can see, as batch size doubles, the throughput first grows and converts because GPU did not fully saturate until batch size reaches 512. By contrast, the latency is almost unchanged at first and then goes up proportionally to batch size. This clearly shows that choosing a suitable batch size can produce very good latency as well as high throughput. And 512 is the most effective batch size for LSTM cell. However, there are challenges for batching RN requests. In general, batching in neural network setting utilizes device SIMD feature to accelerate computation by executing a batch in parallel. Therefore, it assumes that all requests in the batch have the same computation. But this is not always the case for recurrent neural network. If we have 2 requests with the same length, and since each cell step is identical, then these 2 requests share the same computation graph. By concatenating their input, they can be easily batched together. But what if sentences have different lengths? In this case, suppose we have two requests, one has length 3 and the other has length 2. Then how can we batch them? For this chain-like structure, it's straightforward. The state-of-art solution simply passes all sequences to the same length, and now all requests share the same computation graph. This solution is commonly used in systems like TensorFlow, MXNet, and so on. However, in addition to length differences, there is also structure difference. For sentiment analysis, a more powerful model is TRSTM, since a chain cannot fully represent the syntax structure of a sentence. TRSTM structures computation in accordance with the syntax tree of a sentence, which produces much better accuracy. Now the computation is even more dynamic, and how can we batch requests with such dynamic structures? Apparently, padding is not a good solution here. Currently, the state-of-art solution adopted by systems like TensorFlow Fold and DynNet first finds out similar computation shared across requests, and then merge the data flow graph of each request. To have a better understanding of the problem with existing solutions, we first show an example of how they work. Just to simplify, let's assume that some system serves models using batch size 2, and there is only one GPU. At some point, there are two requests in the queue. One has length 3 and the other has length 2. Right now, the two requests have not yet executed. Once the GPU device is available, requests will go through executing stage, computing styles step by step, and finally finish execution and return to user. Now the GPU is ready for execution, and the system has accumulated a full batch of two requests shown in the red box. Then the system starts to execute the first time step of the batch, and then the second time step. While the batch is being computed, more requests arrives. But now new request has to wait until the GPU device is available for execution. When the last step of the batch is executed, although the second request in the batch has finished, it has to wait until the entire batch finishes. Also, the batch is not really full, and part of the computation is wasted, but new requests cannot join the batch. When the first batch finishes, the system has probably accumulated more requests, then the system forms a second batch and starts to compute the second batch. As you can see, the problem with existing solution is that shorter requests have to wait for longer requests in the batch to finish before they can return to user. And even if there are slots available in current batch, new requests has to wait to be executed in the next batch. So to address this problem of existing solution, we propose our approach, cellular batching. Our key observation here is that recurrent neural network is made of cells that are repeated many times. The weight parameters are fixed and shared by all steps during inference. This unique property of RNN inference opens up more batching opportunities. Cells from different requests can be batched together even if they are at different time steps. Therefore, instead of making batching decisions before executing requests, cellular batching makes batching decisions before executing each cell step and allows requests to join and leave execution whenever needed. So here is an illustration. In the previous example, when a new request comes, it waits for the current batch to finish. However, when cellular batching is adopted, once the system finishes the second request in the batch, it allows new requests to join execution, filling up the empty slot to form a full batch. And the system departs the finished request immediately, which avoids short requests being delayed by longer requests. Again, now the first request is about to finish. So if there is more requests available, new request joins the next batch. And once the first request finishes, it leaves the batch. The key observation for recurrent neural network is that model parameters are shared and fixed in serving. And with that in mind, the previous example seems simple. However, in practice, when implementing cellular batching in our prototype system batch maker, we found that making it efficient is challenging and requires careful design. Speaking in high level, our prototype system batch maker has a scheduler residing in CPU, which makes batching decisions and submit batch tasks to GPU worker. Since cellular batching makes batching decisions at each RNN step, it leads to synchronization overhead between CPU and GPU. To mitigate that, we not only need to overlap scheduling with computation, but also need to balance certain trade-offs. I'll talk about this challenge in detail later. Another challenge is how should we handle multiple types of cells? Only cells of the same type can be batched together, and different types of cells should have different priorities. The third challenge is when there are multiple computing devices available, how should we make use of them while taking into account issues like locality and load balancing? In this talk, I will only focus on the first challenge. Now I will use tree LSTM to illustrate how our prototype system efficiently makes batching decisions. Now let's just start with a naive solution. For simplicity, let's assume we use batch size 4 and there is only one GPU for execution. And we also assume that all nodes have the same cell type. Now we have three tree LSTM requests, each has a different structure. Since all leaf nodes don't depend on anything, so they are ready for execution. And we use yellow to highlight these ready nodes. The naive way of batching is we make a batch of the first 4 ready nodes and then submit it to GPU. When GPU finishes execution, we update dependency and schedules the next batch. The performance of this naive solution will be unacceptable because besides the cost of making scheduling decisions, this naive approach stops GPU kernels from being launched asynchronously at cell boundary. And the GPU kernel launching is very costly. But actually, there's no need for the scheduler to synchronize with GPU to make the next decision, because once batched cells are submitted to GPU, the execution order is known, and therefore we know which nodes will be ready for execution. So let's rewind the clock back. After making the first batching decision, instead of waiting for the execution to finish, we update dependency immediately after submitting a batch to GPU. And then we decide the second batch and submit to GPU. And the third batch. Making several consecutive batching decisions in one run not only overlaps scheduling with execution, but also reduces the amount of times GPU is left idle due to kernel launching. Besides, when there are multiple GPU devices available, doing so also improves locality. Then the next question becomes, how many consecutive batching decisions should we make? This is really a hard trade-off because, as you can see, if too many are made at one time, there may be not enough nodes to form a full batch. Therefore, making too many batches reduces the chance to batch new requests. In our evaluation, we found that making at most 5 decisions in one round produces good performance. Now we will show some evaluation results to see how good cellular batching is. We built our prototype system BatchMaker on MXI code base, and we compiled BatchMaker with multiple baseline systems on 3 different applications. In this talk, we will only show results of one application, LSTM, on WMT 15 Europal dataset. The dataset has maximum sequence length 330, and the average length is 24. Experiments were done using the state-of-the-art GPU, which is the NVIDIA Volta GPU. So here, the data flow graph is a chain of LSTM cell. This figure shows the 90 percentile latency versus throughput, and the yellow and the blue lines are MXI and TensorFlow respectively, which are our baseline systems. And the red line is our prototype system BatchMaker. All systems use maximum batch size 512, which is determined by offline benchmarking. As you can see, as overload increases, the latency of baseline systems increase, while our system BatchMaker produces almost stable latency until it reaches performance peak. For a moderate load, when all systems throughput is 10 query requests per second, BatchMaker reduces latency by 93%. BatchMaker not only improves latency, but further boosts throughput as well. For a given latency, let's say 450 milliseconds, BatchMaker increases throughput by 22%. We have very detailed performance breakdown and analysis as well as the results of other applications like sequence-to-sequence model and tree LSTM in our paper. Please do check it out. So let's now talk about the related work. In the background part, we have talked about how current systems perform batching on recurrent neural network. In addition to that, persistent ION caches ION parameters in GPU register files and reuse them for multiple steps to reduce synchronization. This kind of optimization is orthogonal to our work and can be applied to optimize the execution in our system. TensorFlow serving is a system specialized for serving TensorFlow models, which provides flexible interfaces for easy deployment and version control. TensorFlow serving recently introduced batch and unbatch operators, which share similarity to one of our baseline .NET. Many works in database literature try to batch multiple queries together to reduce database scan and share results of common expressions. But our approach is different from theirs because in recurrent neural network, intermediate results cannot be shared across requests. And another difference is that we allow requests to dynamically join and leave a batch. Pipeline execution partitions computation into stages and use multiple processing elements to form a pipeline. However, our approach is different from pipelining because GPU is one single processing unit that is massively parallel. And instead of pipelining to high latency, we exploit the length variance of requests and allow new requests to dynamically join existing requests. Now let me conclude the talk. We propose a new batching approach called cellular batching, specialized for on serving. Cellular batching batches together new requests with ongoing requests. We realized cellular batching in our prototype system, BatchMaker, and experiments show that BatchMaker significantly outperforms baselines. Thank you, and I'm willing to take questions.
Time for a few questions. Yeah. All right.
Konstantin from ETH Zurich. My question is, I understood you applied your approach for inference, basically for forward propagation. Can be your algorithm applied as well for back propagation, and what difficulties you see in applying it for back propagation?
Yeah, that's a very good question. So because the whole point of cellular batching is we leverage the unique feature of inference, which is the weights of ion cells are fixed and shared in inference. But for backward propagation, the weights will be updated for each iteration. And also this approach is targeted for inference latency. But for training, the throughput is the top concern, right? Because training is done offline. Does that answer your question?
Yes.
Okay. Thank you.
More questions? All right, so I have one actually. So I was not clear whether this is the system is supports distributed execution here.
Distributed execution.
Yeah.
So for the results I show here, so when you say distributed execution,
Yeah.
do you
So
mean
if you have a cluster with multiple GPUs with different performance characteristics.
So for our system, we support multiple GPUs. And so although I didn't show it here, we have results for 4 GPUs in our paper. If you are talking about different, like distributing to multiple systems, we don't yet support that. But I guess a naive solution would be we use a hybrid mode and launch multiple instances of our system.
Yeah, so I was more sort of pushing towards, like, I was not sure exactly how the adaptive batching would work in terms of when you have GPUs with different performance characteristics, right? So some of the GPUs have large memory and then they can fit in more batches in. And so how are you going to handle that?
So currently we do assume that the GPU are heterogeneous, but I guess, so basically because for our system we also require us to do some like offline benchmarking to design the optimal batch size for each type of cell. So I guess if the GPU is heterogeneous, then first we need to do like offline benchmarking for each GPU and for each type of cell, and then I guess we can change our system to adapt to that. But I think that will be a future work. But yeah.
All right, so we have one more question. I guess there's a mic behind you.
Christopher Stewart, great work. Can you talk about the sensitivity of the rule of thumb you gave? You said prefetching or looking 5 ahead worked well in your study.
Yeah, we are doing 5 ahead.
Can you talk about the sensitivity with regards to arrival rate or the distribution of arrivals of new jobs?
So actually, so for this throughput and latency graph, like for each point is a different arrival rate. And we did try different number of steps to fuse together. But so 5 is actually very good for like all these workloads. But if you change 5 to like some larger number, then you will miss the chance to batch new requests and the performance will go down. And if you reduce 5 to like 1 or 2, then probably then there will be more overhead in our system. Oh, we assume that the distribution follows the Poisson distribution. So in our evaluation, we didn't try others, but I think we can definitely do that.
All right, so that's it. I guess let's thank the speaker one more time. So the next talk is from the Chinese University of Hong Kong. It is about a system called G-Miner, which is a system for doing graph mining. And it will be presented by Hongzi Chen. And the title of the talk is G-Miner, an efficient task-oriented graph mining system. So.
Good afternoon, everyone. I'm Hongzi Chen, come from the Chinese University of Hong Kong. Today I want to introduce our system, G-Miner, a task-based graph mining system. So the graph data are everywhere nowadays, which is widely used in different areas, social networks, webs, and biology networks, etc. So enhanced dozens of parallel graph processing systems have been proposed in recent years. The one with the most popular one is the vertex-centric model, which uses a think-like vertex design, and each vertex is regarded as a basic computing unit. And Prego, Power Graph, GPS, etc., all the system follows in this design. And edge-centric is another model, and main used in the single machine setting. And regards each enter graph as a streaming edge list. And graph tree extremes, and another system will follow in this design. And another system also follow a graph-centric model, but his computation model is still vertex-centric, but he optimized the communication part and regards each subgraph or block as the basic communication unit, and in order to reduce the total number of messages and the number of supersteps during the job. But actually, the different graph algorithms have different workloads. So the above most systems are armored the graph algorithms with the following features. First, so most of all the vertex will be active in each supersteps or iterations, and the communication cost on each vertex is relatively lightweight. For example, just need to calculate the sum, minimum, or max for the in messages, and the communication and the memory usage are linear or superlinear with the size of the edges of the enter graph. For example, the PageRank connect component SSP are the typical algorithms in these features. However, for the graph mining, it's totally have a different features. For example, the frequent subgraph mining, graph matching, graph clusterings. So not all vertex will be active in the job, and only a partial interest one will the algorithm kills. And compared with the previous mentioned graph processing algorithms, the graph mining workload is much more computing intensive and memory intensive due to the well-known conversion explosion issues. Yeah. In order to better understanding that, we use an example in here, and we deploy a single thread implementation of the max click finding problem and run on high-end servers with 4 different graphs. And we can see that in the later 2 larger graphs, the job cannot finish in 3 days even. And compared with the original graph size, the memory usage is very large. So we can say that the graph mining workloads indeed are very high memory consumption and has high CPU overhead. And we also deploy on 4 existing distributed systems for graph processing, Airbase, Giraffe, GraphX, and GSync. But these systems, some of them cannot finish in time, and some of them have out of memory issues. So for the existing system, the limitation is that they have mismatched of the computation model. Some various design can have very straggler problems for the graph mining workload. And the fine-grained model, for example, centric is efficient and hard to express the graph mining algorithms. And so another issue is, for example, no bound on the memory usage and no optimization for CPU utilization. So what we propose is a task-based system, and for the distributed graph mining algorithms. And we first propose a task model, and based on task model, we propose the task pipeline to further improve different resource utilization. And we have a memory bound in order to guarantee the load balance, we also proposed a BDG-based partitioning strategy, and task student is used to guarantee the load balancing dynamically. And we also propose optimization to improve the scalability of our system, because the graph mining is totally the CPU intensive. So task model, our focus is the following 5 categories of graph mining problems, and we want to provide a unified programming framework for such graph mining algorithms. So we summarized the above algorithms and proposed a general schema. Init is used to generalize the seed vertex from some initial and the update is to recursively process on each subgraph G. For example, to growing current subgraph, or shaking, or splitting, or delete if the subgraph is proving out. So our model is to use each task as a basic computing unit, and each task has the following 3 units: field, subgraph G, which is used to keep the topology of the intermediate results, and candidates to show which task will be interested in the next round, which will be local assessed in the next round, and the context is used to record the metadata. For example, for the graph matching, and in the init, the subgraph in the initial part will be initial as vertex 3, because only vertex 3 has label A, and the candidate will be set as the one-hop neighbors of the vertex 3. And in the first update operation, we will care about vertex with label B and C in the second level of the pattern graph. Hence, the vertex 2 and 3, vertex 1 and 2 will be filtered out because the label are not B and C. We only care about vertex 4 and 5 and involve these 2 new vertex into the current subgraph. And we update the candidate to the 6, 7, 8, and 9 because they are the first, because they are the one-hop neighbors of vertex 5. So for each task, we also have 4 states. Active, which means this task is being processed, and inactive, which means this task is waiting for vertex pooling by the network. Ready, which means the current task and all of the candidates can be local assessed and ready for the next round of processing. Dead, which means this task is finished its job or have been premium out. So once a task finishes current round of updates, if he's still in the active stage, he can directly keep him running until they states converge into inactive. So there is totally no barrier in our system. And we proposed another task pipeline. The main purpose is to celebrate the 3 major operations in our system: CPU and communication, and network communication, and disk I/O. And because the graph mining workload is totally CPU intensive, hence we want to make the communication and disk I/O overhead behind the CPU communication. The task pipeline proposed, we have 3 components in the task pipeline, which is task store, candidate retriever, and the task executor. So the task store manages all inactive tasks in a queue, a disk-based queue. And, but we know that there's a cache in the candidate retriever, which is used to repeatedly vertex pooling. So there's issues in here. If we didn't define the order in the task store, we will randomly pop out the task, may cause a very poor cache hit rate. So we defined a priority queue, which uses a locally sensitive hashing technology to give an order for the task in order to order the tasks which have common non-local candidate vertex to locate all these tasks and nearby with each other in the sum block on the task queue. And the candidate retriever covers all non-local vertex pooling by the network. And once all the non-local vertex have been pulling back into the local machine, which means that this task is ready for the next round, we will prepare this tasks to pop out from the candidate retrieval queue to the next one queue. And we mentioned a little bit our catch strategies. For each catch the vertex, we record a reference counting for how many tasks in ready or active stage referring to the current vertex. Once a vertex with a reference count equals to 0, we will not directly deleting this vertex. Instead, we will remove this to the tail of this cache. Because the one property bring from the priority queue is even the task, even a cache vertex has none refused the task, but this still has some probability to be refused again by the following task. So all the ready tasks will be further processed by the communication queues in parallelized by different threads and to execute to update functions until the states become inactive or dead. Then we will merge it to a task buffer and further merge into the first task in the priority queue in the task store. So our system architecture adopts a master-slave shared nothing architecture. And the master only needs to handle the graph partitioning strategies and the task steering and coordinating and the progress scheduling. And the worker only need to handle the task processing by CPU. We propose the aggregator design in here, which is based on the graph mining features, which can access the context of each task for the global communication. For example, in the max click finding problem, maximum aggregator can be used to record or define or notify all workers for the current globally max size of the click have been defined, which can be used to help the local pruning each workers in order to reduce the search space. And we also propose two different strategies to guarantee the load balance. The first one is a static one, which is the partitioning algorithm. The high-level idea is to cut the current graph into fine-grained blocks, and based on the locality of different blocks, use the gradient algorithms to assign different blocks to the different workers. Please check out the papers for the details about this algorithm. And we also proposed a task steering design to dynamically guarantee the load balance. We first proposed the cost model on task in order to emulate whether this task can have a cheap cost to be migrated from one worker to the another one. And there's a master can monitoring the current process on each worker. Once some condition is met, we will trigger the task migrations amongst each worker to guarantee the load balance. We propose a very simple API. The user only need to implement the init and update functions in two different basic class. So there's totally no details user need to care about distributing computing. Only need to focus more on the graph mining algorithm logic details. We use the graph matching algorithm in here. Only a couple of lines need to write in here. So as for the performance, we use the following 5 applications and ordered by day workload. Triangle counting, max click finding are lightweighted algorithms. Graph matching are a little bit more heavier. Community detection and graph clustering are the most complicated algorithms. And we deploy on 5-node cluster and use the following 6 real-world graph. So as the result shows that our G- system can always beat another existing 4 graph processing systems and on triangle counting and max click finding problems. So, G-Syncer can have a comparable result with us. Hence, we further compare with G-Syncer on graph matching problems. But honestly, in the following 4 sets, we still can show very obvious advantages over G-Syncer in such a heavy mining job with better CPU utilization and memory network efficiency. So we show more details in here. In one job, on the graph matching problem on a friend list of such a very large data set, our job can always keep a high CPU utilization and during all enter jobs, and the network usage will be reduced with time goes by because thanks to our efficient cache design. We use the cost to measure our scalabilities. So as shown in the figures, the cost number of Gminer is very low based on different 4 workload. So we proposed a very expensive structure and API according to our task model. And our system shows outstanding performance achieved by our task pipeline design. And we also further propose some optimization in order to guarantee and improve the system scalability and the load balance. Thanks.
Thanks. So we have time for a few more questions. A few questions here. So I'll just start, I guess. So I was wondering how this sub-graph-centric model has been proposed before as well, right? I think in SOSP we had a paper called RAPSQ, which was pretty much exposing the same programming model.
Yeah.
I was wondering, how do you differentiate with them, I guess?
I think we first, in high level, we proposed a task model. And so this task model can totally separate the CPU, disk I/O, and the networking operations in different parts. And we defined a task lifetime in order to work together with our task pipeline design by the definition of the task lifetime. And we further performed some distributed design, for example, the load balancing operation to further improve the, for example, our whole performance and the scalabilities.
Okay. Any questions further? All right, so I can ask one more, I guess. Oh, yeah, there is one. There.
I went over your the papers, and I actually have one question about your task model. So you assume that each of the task models can be executed in parallel, as they have the second round context, whatever something. But it looks like it is very difficult to find out the different subgraph which can be working in parallel. Like the graph partitioning is usually very hard to do. And in your case, there is no information about how you're going to actually make the subgraph to be incarnated as a one task model. So do you have any specific information or provide some more details how you're going to make the task model?
Okay. So I think use this example to explain with more details can ask you a question. So actually, our task model can be regarded as a staleness. So this is the most difference with another system. Because of the staleness, so all the tasks can be processed in parallel, and even because each task is generated by start from a sitting vertex or a group of a sitting vertex. So and for each round, such subgraph will be grown. Normally will be grown by the next for the nearby one hop neighbors. So for each round, they will group one hop neighbors and with some filtering functions to find out the interest vertex chaos by the specific graph mining algorithms. Because the context records the local states, so there's totally, we don't need to design any barrier amongst different tasks. So, because the graph mining workload is totally CPU intensive, so So our more highlight is we want all the machine to fully use of the CPU resource to focus more on the computation. For the disk I/O overhead and the communication overhead, totally can be highlighted from it behind it.
Okay, I mean, let me define my questions very simple way. So if you see this example,
I think in the interest of time, let's take it offline because I think we need to meet the deadline for the banquet today. So I guess, so let's thank the speaker one more time. So just to remind you all that we will be starting, just after this talk, we will be starting the General Assembly right here. So, and the plan is that we finish by 6:30 and then we go to the boat or walk to the banquet center, right? So the last talk of the day is from a joint collaboration with Microsoft Azure and UIUC. And it is a paper about the microservice framework that is offered by Microsoft Azure. And as you can see, that is a long list of authors, but the paper will be presented by Shagufta. He's a PhD student advised by Indy at UIUC. And the title of the talk is Service Fabric, a distributed platform for building microservices in the cloud. And may I ask the AV guy to actually shrink down the screen? Yeah, that would be great. Yeah. All right. All right, let's start.
Okay. Hello, everyone. Today, I will present our paper on Microsoft Service Fabric. This paper is a collaboration between University of Illinois, Urbana-Champaign and Microsoft. Microsoft Service Fabric is a distributed platform for building scalable and reliable microservice-based application. It's a very old project which evolved over more than 15 years. Many production systems, both inside and outside Microsoft, run on top of it. For example, Skype, Cortana, Microsoft Intune, Microsoft IoT Suites, Azure Cosmos DB, BMW, TalkTalk and many more. Microsoft Azure SQL DB, it hosts 2 million DBs containing 3.5 petabyte of data, which spans over 100K machines. Azure Cosmos DB utilizes 2 million cores, which spans over 100K machines. And Microsoft Cloud Telemetry Engine, it processes 3 trillion events per week. So the question is, how did we build such a framework that supports such large scale, consistency, and fault tolerance? In today's presentation, I will try to give you a very brief overview about it. But before jumping into the details, let me show you the high-level picture. This is the diagram of typical monolithic architecture, where this application consists of UI, database, and business logic. In such approach, the DB is typically connected using a cache. There is a load balancer, which in terms of high demand, deploys multiple instances of the entire application. Therefore, it's bulky and it's not cloud-friendly. On the other hand, in microservice-based architecture, the entire applications are divided into smaller components called microservice. There is a microservice manager that deploys this microservice into an array of containers. In case of high demand, this manager deploys more instances of only the necessary microservices. Therefore, it can scale individual components, which makes it more agile and cloud-ready. Our Service Fabric, this is such a microservice orchestrator that allows full lifecycle management for microservice-based application. Some of the goals of the Service Fabric are, it supports strong consistency from ground up way, where higher layers utilizes this lower layers consistency guarantee and they focus on their own notion of consistency. It's fault tolerant and it supports for stateful microservice, where in Service Fabric, each microservice can have their own state. The first two goals are followed by each subsystem And here are the main subsystem of Microsoft Service Fabric. Due to time constraints, we will only focus on the following three major components, where this federation subsystem, this is the core heart of Service Fabric, and on top of it, the reliability subsystem, and top of it, it's the reliable collection. I will mainly focus on the federation subsystem and give you a very brief overview about the other two. Reliable collection, it's basically a distributed data structure, which, similar to a dictionary or queue, that is highly available, fault-tolerant, persistent, and transactional. To ensure these properties, it relies on its immediate lower layer, reliability subsystem, that manages reliable primary selection, consistent replica set, failover management, and replicated state machine. To ensure this, the layer reliability subsystem depends on its immediate lower layer federation subsystem, where this reliable failure detector and routing token forms routing consistency, which in turn solves the leader election problem. Thus, the higher layer benefits from the lower layer exporting their notion of strong consistency. Now, I will briefly cover the federation subsystem. In the federation subsystem, these nodes are organized in a virtual ring consisting of 2 to the power m points. Here, keys are owned by the closest node. Each node maintains a neighborhood, n successor and n predecessor. This ring ensures consistent membership and failure detection, consistent routing, and leader election. This consistent membership and failure detection follows these two design principles. The first, here, memberships are always strongly consistent, which means that for each node, all of its monitors agree whether this node is up or down. And it decouples this failure detection from failure decision, which is a really unique way using arbitrator-based approach, which I will cover in my next slide. Here, we are using a lease-based monitoring, where two nodes, node A and node B, if node A sends a lease request to node B, and node A receives this corresponding acknowledgement, then node B considers this lease as granted. But instead of a one-way lease monitoring, here we are using a symmetric monitoring, where both nodes A and B maintains this lease simultaneously and independently. Each of this node maintains this symmetric monitoring with all of its neighbors. And if at least one of these leases fails, that means the failure detection, it asks for an arbitration, that means the decision part. Let's see how this decoupling of detection and decision is done using the arbitrator. But before that, I want to make it clear that for simplicity of this slide, here I am presenting a very simple arbitration scheme, consists of a single arbitrator. But in real production, we have multiple arbitrators maintained in a quorum-based approach. I will, for more details, I will ask you to take a look at our paper. So here, two nodes, A and B, they fail to renew their lease, this symmetric monitoring. Then, once they detect this failure, immediately they will ask for an arbitration. In this example, say node A's request comes to the arbitrator first. Now, if node A doesn't receive any reply back from the arbitrator within a certain time bound, it will simply go away from the system. On the other hand, if it receives something, it will simply follow the arbitrator's decision. Now let's see how arbitrator decides. For the decision, in this example, arbitrator receives this request from node A first. Therefore, this arbitrator maintains a log where it marks node A as up and node B as down. And it propagates this decision to node A. When node A receives this decision from the arbitrator, it knows that, okay, for sure, within some predefined time bound, node B, even if it's alive, it will not stay in the system. Let's see how is it ensured. Because the symmetric monitoring failed, node B will also detect the failure and it will ask for an arbitration. But the arbitrator already makes some decision about node B. Therefore, arbitrator will immediately reject node B from the system. Thus, decoupling this detection from decision ensures consistent failure detection. In our ring, this, unlike other P2P distributed hash tables, the service ring maintains both clockwise and anti-clockwise routing entries. In SF routing, it provides more routing option. It routes messages faster. But before that, let me clear it. In the latest design, This SF routing only used for bootstrapping and discovering routing when a node starts up. After this discovery, node can communicate directly. This SF ring ensures consistent routing, which ensures that at any given time, all messages sent to key K will be received by an unique node. If that node crashes, a new node will come up and take that responsibility. This consistent routing provides implicit leader election. For example, in the entire system, the node that owns the key for K equals to 0 is the leader. To ensure this, here each node owns a routing token, which is a portion of the ring whose key it's responsible for. SF ring ensures this following consistency property for routing token. The first, it's always safe. There is no overlap among this token owned by nodes. And eventually every token range will be claimed by a node. It can also efficiently handle node join, leave, and fail protocol. We haven't explained it in our paper. Now, this service SF ring, it's being used for production for more than 15 years, and it's working successfully. So hence, we haven't had to change it. But it was invented concurrent with cord and pastry. But note that cord, pastry, they do not support strong consistency. Now, I will give a very brief overview of the reliability subsystem. The reliability subsystem provides replication, high availability, load balancing. The consistent lower layer, that means the federation subsystem, helps reliability subsystem to easily implement these guarantees. Next, I will very briefly introduce the reliable collection. Reliable collection is Service Fabric's distributed data structure that is fault-tolerant, highly available, persistent, and transactional. It leverages this lower layer guarantee, which is the main goal of the Service Fabric, and like failure detection, leader election, and load balance, etc. It is used in stateful microservice. Now, I will jump to the evaluation part. Here, we evaluate our Service Fabric's arbitrator-based approach with an arbitrator-less approach, where if a node fails to maintain lease, it will gracefully leave the system. It is a fully distributed way of maintaining strong consistency. In both of this case, we varied this total number of neighbors. In this experiment, we deployed 2 rings, consist of 64 nodes, and then selected few nodes and intentionally crashes them. The x-axis shows the node ID that were crashed, and in the y-axis, it shows that what is the total number of nodes that was finally forced to leave from the system. We can see that our arbitrator-based scheme, with high accuracy, it can always detect the exact number of nodes. When we crash 4 nodes, only those 4 nodes were forced to leave the system. On the other hand, in arbitrator-less scheme, say when the total number of neighbors is 4, when we crash node 1, this node 1, along with all its 4 neighbors, that means total 5 nodes, were forced to leave the system. And this number increases when the number of failed node increases. So therefore, it is prone to cascading failure. There are some scalable failure detectors, which are not similar to SWIM, which are not strong. There are also some strong failure detectors, like virtual synchrony, which are not scalable. But our arbitrator-based failure detector, it is scalable. It is a strong failure detector. It prevents cascading failure, and it doesn't depend on the total number of neighbors. Next, we analyze this reconfiguration event, where we collected total 20 days of reconfiguration traces. We classify this event into 3 categories: failover, swap primary, and other, for example, swap secondary. Note that only the first 2 affects this availability. Next, in the graph below, we measured the reconfiguration delay taken by each category. Typically, the cost of strong consistency is high latency, but as you can see, Service Fabric scheduling latency is typically in a couple of seconds. But to make it clear that currently it is dramatically optimized to 100 of milliseconds. Now, I will give a summary of all of our evaluation. For details, please take a look at the paper. Our arbitrator-based strong failure detector, it is scalable. It It has minimum failure detection overhead. It prevents cascading failure. It uses less arbitration meshes compared to our arbitration less scheme. It doesn't get affected by the total number of neighbors. Our reconfiguration, here control decisions are generated quickly within 1 to 2 seconds, and our service fabric's current reactive reconfiguration approach is ensuring availability for 10 million microservices. In terms of message delay, even in the presence of higher churn, message delay remain largely unaffected. And our SF routing, it ensures higher, even though it requires higher memory than CORD, but here message takes fewer hops. As a result, here routing are faster. In summary, I have presented Service Fabric, a distributed platform that enables building and management of scalable and reliable microservice-based application. I have also presented how Service Fabric ensures strong consistency and fault tolerance from lower layer, which helps us to build state in the upper layer. And I have briefly covered 3 core components of Service Fabric: federation subsystem, reliability subsystem, and reliable collections. The Service Fabric code is now open source, and you can check it from the GitHub link. So this was a brief presentation about this paper, and I'll love to take any questions.
All right, thanks to the speaker. Great talk. So we have time for questions now. Yeah, there is one in the back.
Hi, hello. So could you elaborate a little bit of what happens when the arbitrators fail? What is the behavior?
Sure, that's a really nice question. So, as I said that in our case, okay, you give me a scope to explain more in this slide. This arbitrator, in real system, there are multiple arbitrators. Say there are 5 arbitrators or 11 arbitrators or number of arbitrators. Then these nodes are parallelly sending this arbitration request to all the arbitrators. And then the arbitrator makes independent decision. Say for example, node A, there are 11 arbitrators. Node A sends this arbitration request, and node B sends this arbitration request. Node A receives 6 alive response, and node B receives 5 dead response. Now, as the quorum is on node A's side, node A will stay in the system, and node B has to leave the system. Now, the question is, what if arbitrator is dead? Because of multiple arbitration, it's fault tolerant, but if the quorum number of arbitration is dead, yes, that's true. In that case, if there is if any node fails, it will try to communicate with this arbitrator. It won't be able to make this quorum, therefore, it will leave the system. So actually, yeah, in that case, the entire ring will die. But that's a really exceptional case in our scenario.
So let me do a follow-up, which is, so if all the nodes need to send a message to all the arbitrators,
okay,
if that's the case, how is the system scalable with the number of nodes?
Okay, the interesting part is that here, nodes are communicating with this arbitrator only when they detect the failure. So it is a really rare case where all the nodes detect failure as each other and they will send this arbitrator. Yeah, if that somehow happens, in that case, this arbitrator will be congested. But actually, the design is we have implemented in such a way that it's extremely rare incident.
Thank you.
You reported the latency right here. You reported the latency for various recovery operations. Has anyone taken a look at how those affect service level objectives for the higher level microservices built on top of this?
Sorry, can you please repeat?
How do these operations affect service level objectives for the microservices built on top of this?
Okay, so here, this is the latency, this is the end-to-end latency. So if a microservice fails, if a secondary service fails, then it can always communicate with the primary and it can read this data. But if a primary fails, or if because of this congestion, if you need to swap the primary to another place, in that case, there is a slight amount of unavailability period. But yeah, the end-to-end unavailability period is from 1 to 2 seconds in all of these cases.
All right, more questions? If not, then let's thank the speaker one more time. So this concludes the session, and I will hand over to Peter actually for the General Assembly.
Yes, so for the General Assembly, so please stick around. So we're going to start in a few minutes.